Hello everyone, welcome to the Useless Stuff Shop. I'm Bort, and in this series of videos I am electrifying my fishing kayak. I hope that you'll join me. At last, my box has arrived. My project can get started. And life is like a song. I am really excited about this project. I've been wanting to do this project for quite a while. It is a huge project, and it is going to span multiple videos because it would be impossible to cram it all into one. So, the three main parts will be building the battery box, the trolling motor and motor mount and through hull wiring, and the third part will be fabricating solar charging canopies that provide charging, obviously, for the battery and also shade for the occupants. The kayak in question is a feel-free Lure 2 tandem. I'm not going to show you right now because it's in store and it's really difficult to get down. But if you want to look it up, you can look at that for reference and for the moment see what it is that I'm going to be dealing with. The first part of this video series, the battery box. This portion of the project is big enough that I may end up dividing it into even smaller parts. We'll see how that goes. Where I'm at with the project right now is I've actually already done a lot of preparatory work, and I've even built an entire battery box already. I'll salvage some of the parts for it so that I won't be fabricating everything from scratch for this video. The new box that has finally arrived and allows me to get started is this one. It's a fairly well made dry box. Big enough to accommodate the battery and some extra electronics. While I am breaking the project into multiple manageable pieces, none of the pieces can be completed in a vacuum. None of them can be completed in ignorance of the other parts. So a lot of preparatory work has gone into arranging the components within the box, being able to sight the box within the kayak, and making sure that everything is going to fit, planning out the cable routing, and so on. The box, for its part, needs to provide a central location for the battery and its ancillary components. It needs to provide portability, safety, protecting the electronics from impact damage and water damage. It needs to provide convenience. And all of the features that I'm going to build into it are related to achieving those goals. The central component of any battery box is, of course, the battery. I want to use this 12 volt, 100 amp hour lithium iron phosphate battery for this project. What I like about this particular chemistry is its deep cycle capability. It can go to 100% discharge or near 100% discharge without any potential for damage. And its cycle life. Some of these batteries, if they're well made and well maintained, can go as many as 7,000 cycles and have a 10-year lifespan. 7,000 cycles, if it got that many, even 2,000 cycles. That's a lifetime of boating for me. So this could potentially be a lifetime battery. The way, and they're also a third the weight of lead acid. So three really great advantages. The way that this system will go together is the first thing in line from the positive terminal of the battery is a 100 amp marine circuit breaker. This is necessary to protect the battery. It has a 100 amp maximum continuous discharge, and the circuit breaker is sized as a compromise to both protect the battery and to not trip on a hot day when the system is at full load, meaning the trolling motor is at full throttle and all of the auxiliary outputs are also operating at full capacity. So we'll just draw this here on the workbench. That's a 100 amp route right there. Next in line, in the same circuit in series, is a waterproof 120 amp circuit breaker. This is sized a little bit larger so that it can switch under load without damaging the contacts. And then downstream from that we start to get to outputs. The first is a 60 amp marine circuit breaker to protect the trolling motor output. The trolling motor has a 52 amp maximum current, and I want to be able to wire out to that with this fancy 50 amp waterproof connector. And I'll go into that style of connector in a little bit. There's some interesting challenges in working with that. The next set of outputs is through this fuse block. This is a 6-way fuse block. It has a bus bar on the bottom for a common ground, super convenient. And from this I have 4 outputs and 2 inputs. One of the 4 outputs goes back inside the box to power some stuff inside the box that I'll get to in a moment. The other 3 outputs will exit the box through a similar, smaller connector. This is a 7 circuit connector instead of 2, and I'll use 6 of the pins on it. And these 3 circuits will be for 2 USB charging devices for whatever USB accessories, one for each of the 2 Kayak occupants, and one for a fish finder. The 2 inputs, these are both from battery charging sources, and I wouldn't normally mix the goes in's and the goes out's within a fuse block, but this is a really space constrained application. So I have to kind of cross the streams a little bit. I'm going to use this SAE connector for AC mains charging. So this will have its own input. I have a 10 amp lithium iron phosphate charger that just plugs into the wall. So I'll use that for charging on shore. I mentioned solar charging on the boat. So this is a 300 watt MPPT lithium iron phosphate solar battery charge controller. Does that fit in the picture there? Yeah, kind of. So there's an input from that, and it will have its own little waterproof connector. I don't have the mating connector to show you because it's elsewhere right now. Now on the return side, I have this shunt, and this is used for current sensing. What a shunt does is it introduces a small resistance into the circuit, and what that does is it allows current measurement by measuring the voltage difference across that resistance. So this goes back in here from all the ground lines from all of these other circuits back to the negative terminal of the battery. And the other part of this is the battery monitor. I really like this battery monitor. I've done some testing with it with some lab instruments I borrowed from work, and it's fantastic. It actually meets its own specifications. I was really pleased with that. It's accurate, it's consistent, it's reliable. I love it. It uses this current sensing shunt, and what it does is it calculates the actual amp hours and watt hours consumed from the battery, and it works in both directions. So it will display the current battery capacity, and it accounts for both discharge and charging currents. It's super cool. This will be cabled, let's see, how can you see that? Outside the box through another pair of these little waterproof connectors to this panel, which will be externally mounted in front of me in its own 3D printed box, so that I don't have to contort myself to turn around and look behind the seat where this battery box will be situated. Controlling the relay. I want to use this nifty little light up waterproof power switch to control the relay. It's a push button type. And in that same circuit, to the relay solenoid, I'm going to put this in there in series. And this is an emergency kill switch. This is tethered to the operator, and should the operator fall overboard, this will disconnect, open the circuit, and open the relay so that it will kill the motor and everything. That way, the kayak doesn't just cruise away if I fall overboard. There will also be a couple of LED indicators that I don't have handy right here. Anyway, they're panel mount LEDs, and I will wire them across these two circuit breakers so that if either of these breakers opens up under load, the LED will light and indicate a fault. About the connectors I've chosen. So these are a pretty slick IP65, IP67 waterproof, dustproof connector. They're a bulkhead panel mount on one side, cable on the other. A lot goes into choosing the connectors for this project, because they need to be pretty well environmentally ruggedized, they need to be dependable, reliable, and they need to be able to protect me from myself. And that is part of the reason for making them all different. Obviously a higher current connector is going to need to be larger, but for the low current connectors, it's not just the number of circuits that I've chosen to be different. This connector for the solar charging, for example, has 2 pins, and it is a female receptacle. This 7-pin connector for the outputs is a male receptacle. These differences, and the visual differences in color, for example, help me to protect myself from doing something stupid, from trying to mash connectors together that don't go together when I'm not paying attention. There's another facet to this connector selection. While these connectors are really cool and they're more or less affordable, they're still a little pricey. Getting cable that will actually work with them has proven to be an interesting challenge. Because, as you can see here, the cable gland is round, circular, and it only accommodates a certain range of outside diameters of cable. So, selecting a cable that is the right kind of cable for outdoor use, or marine use, even better, has the right number of conductors, can carry the appropriate amount of current, and has a round cable jacket, not just a collection of wires, has proven to be an interesting challenge, and I've had to put a lot of work into it. Oh, and there's another constraint on that. That is cable that is available to me, that I can actually buy. I can go to a cable manufacturer's website and I can spec out a cable that is exactly what I need, but I can't buy it in quantities of less than 1,000 feet. I can't buy it in less than a spool quantity. and some of those spools are several $1,000s a piece. That's a total non-starter. So I've had to make a lot of compromises. One of those, with this cable, this is the high current cable to the motor. 2 conductors. I've spec'd a cable that is actually an outdoor rated extension cord cable. This is a 4 conductor 10 gauge cable. Has a round jacket, and 10 gauge is not enough to carry 50 amps. What I've done is I've paired up the conductors so that I actually have 2 pair of parallel conductors. As far as electrical code goes, it's pretty sketchy. It probably violates every electrical code on the planet. Functionally, it's totally safe and will work. I calculated out the wire cross-sectional area and the resistance and the power loss in the cable and all that, and it's all perfectly fine. This cable, this one right here, this is an 18 gauge 6 conductor cable, which is just about right for the pins inside the connector. But the cable jacket is too small for the cable gland. So I've had to build it up, you may be able to see that, with a couple layers of adhesive lined heat shrink in order to keep it round and to increase the diameter to the point where the cable gland can actually seal around it and be watertight. This is the other end of that solar charging connector. It's already on a cable, like here. This one actually just happened to be just about the right size, but again, this is a repurposed extension cord cable, and it's a 3 conductor cable. So one of these conductors is a no connect, it's unused. I'm only using 2 of the conductors in it. A little sketchy, I don't like having to do that, but I'm constrained by being just a hobbyist. So now I want to talk a little bit about space constraints and the physical location constraints placed on all of the components. This is a real 3D jigsaw puzzle to get the whole thing together in a manner that will actually work. As you can see, this box, while it looks physically fairly large, is not that much larger than the battery itself. This is intentional, but it also provides a bit of a challenge. How do I get everything in the box in a manner that will both physically fit and function? I also have the constraint of placement within the Kayak well to work around. The Kayak well comes up to about this level that I sort of hastily sketched out here. And in addition to that, there's a rod holder in the well right here. So fishing rods will come up at this angle at this location. So this is the end panel space that I have on each side to work with. And I do want the connectors on the end panel. I think that's where they'll work best. And yet another constraint on connector placement are these gussets, reinforcing gussets. I have to work around those. I don't want to remove them because it will look like ass and it will weaken the box. To give you some idea what kind of a puzzle this is, I want to show you the 3D model that I built to plan out component placement. So this volume represents the interior surface and interior volume of the enclosure. And we have all of these little bits mounted to it and within it. The big block in the middle, of course, is the battery. And there are a number of constraints to work around in placing all of these components. So we have the draft angle of the enclosure, the space that is left over around the battery. We have the depth of the well in the kayak, which comes up to about right here. And we have the size of the components themselves. So, for example, the relay.
circuit breaker. These parts cannot be placed any lower because of the draft angle of the enclosure and because of their own height. They would interfere with the battery. Some other things that are a little bit more subtle have to do with the wiring. So some of these high current connections in particular have large diameter and fairly rigid wires that have a large bend radius requirement. The motor connector right here has two 8-gauge wires that come in the end, and they need to have space to route around to this relay and to the terminal on the current sensing shunt. Similar situation exists with the SAE connector. Like the motor connector, it protrudes a long way into the enclosure and has wires that come out of the end. They're fairly large gauge and fairly rigid. In this case, I don't have a better placement for this, and there will be some interference here with the cover on the fuse block. That's just unavoidable. I don't have any other place I can really put it. So you can see what kind of puzzle this is. It's fairly challenging. Here's another one. The power switch has wires that come out the end of it here. So this power switch needs to be placed in an area where those wires won't be crushed up against something like the battery. And there is an additional component that isn't represented here, and that is the hold down bracket that goes across the top of this battery that holds it in place, which sticks up a little bit above the surface of the battery. So the placement of the switch has to avoid that as well. One component I haven't talked about is this panel. This is a 1/4 inch thick HDPE plastic panel that I have milled to attach these components to. And the purpose of that is that these components collectively require a very large number of mounting holes. If I bolt them to a panel and then bolt the panel to the enclosure, then I greatly reduce the number of mounting holes and therefore reduce the number of potential water ingress points. This panel, as it's represented, has 8 mounting holes. I may not need to use all of them, and I'll cover more of that as the project progresses.
The electronics mounting panel that I mentioned, I already have one. Actually, I already have 2. These were salvaged from the first enclosure, where they served a dual purpose. This one was on the front wall of the enclosure, and it served primarily as reinforcement. The other was both reinforcement and provided the mounting for the electronics. I want to repurpose this. I don't want to have to make it again. It took a lot of work. However, I do need to modify it just a little bit because it is a smidge too long. So I'm going to take about a 1/4 inch off of each end. Now I have a panel that fits the flat portion of the interior wall of the enclosure. Fortunately, both this box and the previous box have about the same draft angle here, so I didn't really have to fiddle with that at all. I just needed to slim it down a little bit because the radii at the corners are a little larger in the current enclosure.